start today's seminar. Today's speaker is Merlin Reichard, and he will talk about dark matter direct detection via electromagnetic multipoles. Please start when you're ready. Yeah.
Thank you. So first of all, I would like to thank Professor Munich for giving me the opportunity to be here at KIRAS and to present my work. Okay, so briefly about me, I'm Merlin. I'm a PhD student from the Technical University of Munich, and my supervisor is Alejandro Ibarra. So the majority of this talk is going to focus on this first work here. So this came out of this collaboration with Alejandro Ibarra and Rio Nagai. And then also in the end, I will briefly talk about work in progress, again with Alejandro, with me, and Gaurav Tomar. Okay. Okay, so the general topic, let's say, of this whole research project, let's say, is to qualitatively answer this question, or to qualitatively have some, to gather some knowledge about this question, which is how dark is dark matter? So dark matter is dark, okay, sure, but what does it actually mean from a quantitative point of view? Okay, so here I show a picture. So I ask one of these AI image generators how a dark matter particle interacting with the electromagnetic field could look like, and it generated this very beautiful picture. So maybe we will at some point have a theory which predicts exactly this picture. Probably not, but this may be in some sense an inspiration. Okay, so let's go to the outline. So in this seminar, I'm going to briefly motivate dark matter and dark matter direct detection experiments. Then I will talk about electromagnetic moments. So first I will briefly recapitulate the classical multipole expansion in the electrodynamics. Then I will talk about electromagnetic moments of fermions. And then I will talk about this one loop calculation of the anapole moment. So I will also explain before what the anapole moment is. And then in this third part, I will talk about the application of this one loop calculation to the lightest neutralino. So both in simplified scenarios and within the full minimal supersymmetric standard model. Then I will talk about the connection to direct detection searches of dark matter. And then I will talk also about the dipole moments of Dirac fermions. And then at the end, I will summarize everything. So let's start. So about the motivation, so there's a lot of evidence out there that we have to have this additional dark component in our universe. So starting from the scale of galaxies, where we know that, or where we observe that the visible matter only cannot be responsible for the observed gravitational or the observed velocity distribution or velocity curves in the galaxies. So the larger the radii are, the constant we observe the stars orbiting the centers. But if we don't have any dark matter contribution, so here this green line is the contribution due to a dark matter halo following an NFW profile. If we don't have this contribution, then we expect this drop off for larger radii. But we don't observe this, so this is one of these one of these observations which lead us to believe that there has to be dark matter out there. And also on the scale of galaxy clusters, so here we have this famous picture of the bullet cluster where we see the center of mass corresponding to the observation in the X-ray does not correspond to the center of mass deduced from the gravitational interaction. Again, showing that there has to be some additional type of matter, probably. And also for the cosmological history of the universe, we have the CMB. Also here, the dark matter candidate plays a very important role. And here we have also structure formation. So we have to have this additional non-luminous component, matter component in our universe for the structures to have formed by now, which we observe. So that's the brief motivation of dark matter. And okay. So now about dark matter searches. So roughly speaking, there is three different ways how we are looking for dark matter. One is via colliders. We're looking at missing states, missing energy leaving the detector. Then there are direct and indirect detection searches. So in direct detection experiments, you're looking at dark matter particles colliding with our targets in our experiments. and then leaving a recoil, for example, which we can then measure and maybe detect dark matter this way. In indirect detection experiments, we're looking for the annihilation products of dark matter interactions in the galaxy or in the Milky Way or other galaxies. So direct detection experiments, this is what I will be focusing about in this talk. And here we're looking at these scattering events. So we have an incoming dark matter particle here at Earth interacting with targets in the detector. So in this context, we can connect this scattering rate. So this is the theory or like the prediction, how many scatterings per energy bin we expect. This is connected to information or to physics from particle physics. So we have this dark matter cross-section here, the differential cross-section, which describes the interaction between dark matter and the nucleus in this case. So N is nucleus. And then we also have to include the information from dark matter. So this ρ0 is the local dark matter abundance, and this F is the velocity distribution here at Earth. So there are these two tasks. So one is we have to know this local information about the dark matter, information, and the other is about particle physics. And then, of course, we don't know how this interaction could look like. So maybe it doesn't interact at all as a target, maybe it does. And one kind of well-motivated scenario is that dark matter interacts electromagnetically. But of course, not trivially, otherwise it wouldn't be dark matter. So we have to have this interaction, let's say, at the quantum level via loop-induced effects. So in other words, we're looking at a scenario like this. So we have dark matter particles chi with some interaction with the photon, here denoted by this mu. This photon is our channel in our, which then mediates this interaction to our target in the direct detection experiments, for example, these nuclei or electrons. So that's the motivation.
Sorry, is there a powerful reason to consider electromagnetic interaction between dark matter and standard particle, or just let's do it? Or
yeah, let's do it. I mean, like experimentally, we only know it doesn't interact at tree level. It doesn't interact like an electron does, right? Otherwise, we would have seen it.
yeah.
So it's good to say about it.
These are higher order terms, like you have dimension 5 terms or 6 terms?
Yes, eventually, yes. But I mean, this is just like from a, let's say, bottom-down perspective. But yeah, we just say, okay, what if it interacts somehow?
Mm-hmm.
Yeah, in the theory later, I will talk about dimension 5, dimension 6 operators, yes. But just a priori, it can somehow interact with photons, right? Nothing forbids it, let's say. Okay, so let's now talk about electromagnetic moments. So from a classical point of view, we can have, so this phi is the electric field potential, the scalar potential. It's just given by the integral over the localized charge density rho. And then we have this denominator. If we now go far away from the source, in other words, we take this r, so where we kind of measure this potential, we take it far away from the source, r prime. Then we can make an expansion of this denominator, like this. For example, this first term, we only have this integral over rho. By definition, this is just the total charge of this charge distribution. So we get here the charge q. And then similar for the other terms. So here we have the charge over r, the electric dipole moment dotted into the separation vector, and so on. So this is this classical multipole expansion for the electric scalar field. And this goes on and on and on. So we have charge, we have dipole, we have quadrupole, we have octopoles, and so on. We can play a similar game for the magnetic vector potentials. In this case, we don't have the charge density, but we have this current in this integral. Again, we can make an expansion like this, and then we can carry out this integral term by term, and we find this expression. So here the first term is not the magnetic monopole, because this is 0, but it's this magnetic dipole moment crossed into this separation vector. And then again, you have multiple orders in this expansion. So that's a very nice, let's say, visualization of what's happening, because you can very well visualize these different terms in terms of a physical setup, let's say. So the first term, for example, first in this electric case, the first term is just that you approximate the charge distribution by a point source. Then you add like this dipole, which is kind of an object like this. Then you have this quadrupole and so on. So term by term, you approximate your charge distribution how it is. And this works because we are far away from the source. Okay, so now let's talk about what happens if you have a charge distribution in the the presence of an external field. So in this case, you can write this interaction energy as this integral over the density of the charge density times the scalar potential of the external field, and then you have the scalar product corresponding to, let's say, the magnetic contribution. So then you can write it as, so the first term is the electric contribution, the second is the magnetic contribution. Again, we can make this multipole expansion, and you find that the energy due to this electric contribution, the first order is due to the charge times the external electric field potential. Then you have the dipole moment dotted into the external electric field, and so on. Again, you have an expansion, in this case, in the derivatives acting on this electric field. For the magnetic case, it's very similar. Again, you have an expansion. Here you have the time derivative of the electric dipole moment. You have the magnetic dipole moment dotted into this cross product, and so on. But now, like there was this very interesting observation, which was summarized here in this paper, that here you find this interesting term at second order in the expansion with this. I think it died.
Yeah.
So there's this funny term with this A. This A is the so-called anapole moment or toroidal moment. So this A. And it's interesting because, as it turns out, it belongs to a completely different family than these magnetic and electric moments. So before we had this electric dipole moment, electric quadrupole moment, and so on. We had the magnetic dipole moment, magnetic quadrupole moment, and so on. And this is part of a completely new family, which are called these toroidal moments.
Sorry. As far as I know, in classical mechanics, there is no anapole. Yeah. In principle, in classical mechanics, we need to call the term as a toroidal moment.
Oh, yeah,
right? Yeah. But strictly speaking, anapole and toroidal is different.
Yeah,
right?
that's true.
Yeah.
But they coincide if you're on the mass shell.
Yeah, the structure is same.
Yeah.
But then in this case, what is the explicit form of a vector? Usually, definitely, I think this is written with the position, right?
Yes. I don't have it here. I can
Okay.
show you later. I mean, it's an integral over.
Yeah, kind of.
It looks similar than this, like an integral or
Yeah.
something like this.
Okay, I got it. Yeah.
Yeah.
Okay.
But I don't have it explicitly.
Yeah.
Okay, and this is kind of how this anapole moment looks like. So in classical physics, you can have this anapole moment like in the lab. If you take a solenoid and shape it like this, like a torus or like a donut, then if you have this current flowing like this, you generate this anapole or toroidal moment T. So that's kind of how you could make it in the lab. Okay, so now let's talk about fermions. So let's write down the most general Lagrangian, or like up to dimension 6, of a fermion psi interacting with the photon field a mu. So the first term is basically, you all know it, it's like an electron or muon has, so it's just a charge. So here Q is the charge. So that's the most trivial interaction you can have with the electromagnetic field. The second term corresponds to the magnetic moment. So also this is well studied. For example, the G-2 of the muon comes exactly from this term. Then you have the electric dipole moment. Also, this has been studied. And then, so these are both dimension 5 operators. And then you also have this dimension 6 anapole operator. And then, if you take the non-relativistic limit, you find these interaction, these effective non-relativistic interaction Hamiltonians. So the first case is exactly the charge times the scalar potential, like the zeroth component of this photon field is the scalar potential. Here you have the interaction between the magnetic moment and this B field with the dipole moment, and then here you have this anapole moment. So this corresponds to this non-relativistic limit. Okay, so this is kind of the setup for the spin 1/2 particles, so for fermions, and also similar arguments hold for higher spin particles. So if you have a spin 1 particle, you can you don't stop at the dipole and anapole, but you can go up to quadrupoles. And if you have a spin 3/2 particle, you can go up to octopoles and so on.
Sorry, I have a question. In this case, just if we solve this Hamiltonian, we can think that spin plays a role as a electric dipole and simultaneously magnetic dipole, right? Because compared to classical concept, if we consider the classical electromagnetic interaction, then the electric dipole and magnetic dipole is caused by the two charges, right? Yeah. But if we go to the quantum mechanics, then in this case, we can think that spins plays a role as a electric and magnetic dipole momentum simultaneously. Is it correct interpretation?
I don't know.
Because I have considered about this. How should we interpret this Hamiltonian? Because in classical mechanics, usually if we consider the dipole, then we should consider 2-point charge. If we consider electric dipole, and if we consider magnetic dipole, then we need to imagine the rotating current, right? But in this case, the coupled operator with magnetic field and electric field is the spin operator, right? So I think I have agonized that in quantum mechanics level, the spin plays a role as a electric and magnetic dipole moment simultaneously. Maybe.
It looks like it, yeah.
Yeah.
I haven't really thought about this. Maybe in some sense what I can say about this is that it makes sense that you have the spin vector because you don't have any other preferred direction in your quantum level, right? So you don't have any other quantity you could actually dot into this B and E field. But yeah, I haven't thought about the correspondence, let's say, to the classical.
Yeah, but just I have organized whenever I studied about anapole documentary, so just I asked you whether you have another idea or not. Yeah. Okay, sorry, yeah.
No, thanks for the question. Okay, let's move on. So earlier I talked about this effective interaction, or like this effective vertex M when I show this diagram. And it turns out you can write it like this. So this is the most general way how you can write it in terms of independent Lorentz building blocks, let's say. So you have gamma mu, gamma phi, sigma mu, gamma phi. And so here in this context, these four form factors appear. So you have the charge form factor, the anapole, the magnetic, and the electric dipole form factor. And typically, because this photon, which is appearing in this vertex, can be off-shell, which means that these form factors can depend on the momentum transfer q square, or the photon momentum q square. And then to, let's say, have correspondence to these classical moments, we always take the zero momentum limit. So we set q squared to 0. So we put the photon on shell, where we then can find that the charge form factor evaluated at 0 momentum should be the charge, then the anapole form factor should be the anapole moment, and same for the dipole moments. And then also, I just wanted to briefly mention that for you to have an electric dipole moment, your UV theory has to break CP. And so this is the general vertex structure for a generic fermion. Now the point is, if our fermion is a Majorana fermion, then the charge and the both dipole moments, they are just 0, just from the Majorana condition. So you only have the anapole moment, which is non-vanishing. So this is basically this whole story about the anapole moment, why it's interesting, because if you have a Majorana fermion, just by symmetries, you know that only the anapole can be non-zero. This is in particular interesting for dark matter, or also for neutrinos, because in many models, they turn out to be Majorana fermions. And also, this is going to be important in a second, or maybe in 10 minutes, that this anapole moment is operator violates separately P and C. Okay, so let's now talk about the one-loop calculation of the anapole. Okay, so we need a UV theory or a UV model to determine the multipoles. So one possibility is that we work with this scalar T-channel mediator. So here in our Lagrangian, we have this Majorana fermion chi. We have a scalar S and a standard model fermion F. And then we allow different coupling strengths to the left and to the right component of this fermion F. So this would be one possibility of a UV model. Then a different possibility is to have a vector mediator. So in this case, again, Majorana fermion. We have gamma mu, we have this charge, the Dirac fermion chi minus, and then we allow different couplings of this Majorana fermion to this charged fermion here. And we have this charged boson. And then also, I will not write it down explicitly, but we also have these Goldstone contributions because these vectors are massive bosons, massive gauge bosons. Okay, and I just also want to mention that this model has not been studied so far, basically. So this is what we did for the first time in our paper. Okay, so now we have our interaction, we have our building blocks. With this UV model, we can write down the amplitude m, so we can write down, let's say, the amplitude at the one loop level. And now the question is, but I mean, it's kind of complicated. I mean, okay, depends on who you ask, but maybe it's a little complicated. You have integral over the loop momentum, then you have like all the vertices, you have the propagators. It's not so easy to actually extract what are the electromagnetic moments. So how do we extract, let's say, all terms which correspond to gamma mu? This would correspond to the charge, or gamma mu, gamma phi, which would correspond to the anapole moment. And same for the dipole moment. And in fact, there's a very neat trick. So we can use the observation that that all of these building blocks of this Lorentz structure make up a basis. So like 1 and gamma mu, they are orthogonal to each other. So if you take the trace of 1 and gamma mu, you get 0. And similar for the other building blocks, let's say. So what we can do is we can define this projector, which basically just has coefficients corresponding to all of these different possibilities. And then we can solve this equation here. So we take the trace of this projector with these 6 coefficients f and g. We multiply it with our generic vertex structure. We take the 0 momentum limit because we're interested in the moments and not in the form factors. And then we say, okay, we want that this should be just equal to the anapole moment, for example, or the magnetic moment or dipole moment, whatever. And with this condition, we can fix all of these coefficients f and g appearing in this projector, which then just gives us a projector we need in order to calculate this moment coming from the one loop expression. So once we have found this projector, we can just take the projector, we multiply it with our one loop expression coming from this vertex from our UV model. We take the 0 momentum limit and we just find a contribution to the anapole. So that's a very neat and trick how you can extract the Lorentz structure you're interested in from this loop expression.
Sorry, would you please explain more again what is the meaning to fix the coefficient Fi and Gi?
Okay, so like depending on which moment you're interested in, these differ. So like basically, like for example, if you want to, I mean, okay, I don't know it by heart, but like it depends. So like, okay, the anapole moment is, let's say, fixed by the Lorentz structure. We need to find all the coefficient of the gamma mu, gamma phi. That will give us the anapole. And this means that if we choose this projector such that it's all the other parts are like projected to be 0, we know automatically everything which remains has to contribute to the anapole moment. So that's why these differ. So like depending on what you choose here, so like some of them could be 0 or so, depending on what you choose, you get the different projectors.
Then how can we obtain the value for this coefficient?
Just solve this equation basically. You can then make like a you can compare the coefficients on both sides.
Yeah. Okay, I got it. Yeah.
I can show you the details later.
Okay.
That's basically the idea. So like you have this condition, and from this you can fix all of these coefficients.
Yeah.
And then you can have, for example, a projector for the anapole, and then you can just dot it into a generic one loop amplitude, for example, and you directly get all the contributions coming from this one loop amplitude to the anapole moment, for example. This also works for the dipole moment.
Yeah. And here the momenta P1, P2 are the momenta of dark matter high.
Yeah, exactly. Incoming, outgoing.
Sorry. Yeah. I haven't seen.
Yeah. Sorry, I didn't explain it. Yeah.
Okay.
So in terms of this multipole, anapole is order is same as quadrupole, or in the classical level.
At the classical level, so like in terms of the derivatives, it appears at the same order. No, maybe here already quadrupoles appear. I think so. Here also, like in this expansion at first order, the derivative already quadrupoles appear. So here, So here these different lines correspond to different orders in their derivative. So 0 is 1 and second, and here the anapole appears in the second order. Oh, can you maybe, does this answer your question? So
in the toroid dipole point of view, this is a dipole, right? Anapole is a dipole based on the toroid moment.
toroidal is not a dipole moment, I think. I think this was
Yeah.
the full discussion, the whole discussion of this paper here.
Yeah.
That they argued it's actually independent.
Yeah.
Okay, here I'm using toroidal and anapole interchangeably.
Yeah.
Sorry if this causes confusion. And so in the picture on this picture you don't have any quadrupole moments for the fermions. So the quadrupoles, they will appear for the spin 1 particle, for example. Okay, so let's go back to these UV predictions. So let's talk about the scalar contribution. So we have this UV T-channel scalar model. We can draw these diagrams. And then you can use this technique I just described. So you take this projector, you multiply the projector with its amplitude, you take the trace, you take the zero momentum limit, and then you find this contribution here, which I call the scalar contribution. And what is very nice is that you can see that it actually requires this parity violation, because parity conservation would mean that CL and CR are identical, in which case this anapole just vanishes identically. So it's very neat to actually find this confirmation here that this anapole is proportional to the difference of this left and right coupling. Okay, and this Fs is this loop function. And so here I show plots of the scalar contribution. So here it shows CL equals 1, CR equals 0. These 4 plots are for different dark matter masses, or let's say neutral Majorana fermion masses, so 50 GeV, 100, 200, 300 GeV. The different colors correspond to different masses of the fermion in the loop. So black is 1 MeV, blue 1 GeV, then 10 GeV.
Go back to the previous slide. So this sky is Majorana, right?
Yes.
And F is not.
No, F is just a standard model Dirac fermion,
I see.
like charged. These are both charged under electromagnetism.
I'm just thinking if you take a vector like fermion, then it would be identically 0, right? But you took a Majorana and okay.
Okay, so there are 2 remarks. Okay, let me finish explaining the plot. So the y-axis is the prediction for the anapole moment in some units. The x-axis is always the scalar mass in the loop in units of the dark matter mass. And now there are 2 observations. One is there's always this enhancement once the scalar mass and the dark matter are close in mass. And the second observation is that the general amplitude is dictated by the lightness of the internal fermion mass. So the lighter the fermion, the larger typically this anapole moment. So this already tells you that, for example, if you have very light leptons, like the electron, or also very light quarks in your loop amplitude, you expect a rather large contribution to the anapole. Furthermore, if your scalar is close in mass to your dark matter, let's say, then you also expect this huge enhancement.
By the way, what is the discrete point for lead line?
Here?
Yeah, no.
Here?
Yeah.
Okay, so basically here in this F, you have a function which is discontinuous around this point. So like somehow this, let's say it's a numerical effect, because you have some discontinuity in this F function. It just shows up like this.
There's no particular physical region, right? Okay.
Except, so this corresponds to the situation where the sum, okay, wait. No, there's no physical reason for that. It's just, yeah. Okay, so let's talk about the second model I was talking about. So this vector mediator. So again, we can draw these diagrams at the one loop order. But now it turns out that this is not completely trivial. Because if you naively calculate these diagrams, okay, again including Goldstones, then you will find that this is UV divergent and gauge dependent. So both of these observations already should tell you that something went wrong, and this is actually not a physical observable. And the culprit, let's say, the problem is this triple gauge vertex here, because this has a gauge dependency. In the arc chi gauges, this is dependent on the gauge parameter chi. And actually, similar problems have been encountered in the past for the calculation of the charge radius of the neutrinos. And in this context, there were two solutions proposed. So one is the pinch technique, one is called the background field method. In the latter, what you're doing is you replace the photon by the background field photon, and then when you work in the quantum Feynman gauge, you find again, or you find a physical well-defined quantity. And now we'll talk about these two methods briefly. So the pinch technique. So basically the statement is that we know that only the full amplitude should be gauge independent or gauge invariant, right? We don't really have any say about sub-amplitudes, and we a priori they don't have to be gauge independent. Right? So this is exactly what we have been observing here. So of course we know that if we look at a 2x2 scattering event, it's gauge independent. So the problem basically comes from how do we assign, or like what, how do we find the vertex in this general amplitude? And this is exactly where this problem came from, because right now we only considered, let's say, the direct vertices coming from the theory as the sub-amplitudes, and they are unphysical. But what we actually have to do, we have to consider the full amplitude and then extract all vertex-like terms from the total amplitude. So in other words, it means that you can have other diagrams which also are topologically equivalent to the vertex, and you have to steal, let's say, terms from these other diagrams. And this is exactly what this pinch technique is doing diagrammatically. So basically, all these terms which you have been missing, it's reassigning to this vertex, and the terms which are missing are exactly the terms which will cancel the gauge dependency. And there was also, okay, apart from this whole discussion for the neutrinos, and also there was some discussion about form factors of quarks. So I can recommend you this review here. There are many examples discussed. But also more recently, there has been this discussion about the electric dipole moment at a two-loop order from these Barzi diagrams in a 2 Higgs doublet model, where they also considered this pinch technique to calculate this gauge independent contribution. Okay, now let's talk about the background field method. So basically here, so when going from the classical Lagrangian, from the classical theory to the quantum theory, here what you're doing is you split up your field. So you split it up into a quantum field, this A, and a background field. So in a typical formalism, you just assign your fields to be quantum fields. Here you split them up. And the neat thing is that when you then write down your functional, you're generating functional, that so this generates your green functions, that these green functions are independent of the background gauge parameter, and that they satisfy QED-like water identities. So from a theory point of view, they are very neat, they have very nice properties. And now there was this very nice observation that if one uses this background field and uses this quantum Feynman gauge, that this is in fact equivalent to using the pinch technique. So again, if you if you have your theory written in this background field formulation, if you use the quantum Feynman gauge, then you find a physical well-defined quantity. Okay. And so we can also visualize this correspondence, let's say. So we are, in the end of the day, we're interested in this amplitude, right? We're interested in dark matter scattering via the photon exchange with our targets. So we have this well-defined physical 2-to-2 process. Now, what we did before naively was that we just took this vertex here, and we found this is gauge dependent and UV divergent. But this is not a surprise, because, for example, this term also contributes to the overall amplitude. So what we have to do is we have to take these vertex terms, we are assigning to this vertex, and then we can properly define this overall amplitude. And this is what the pinch technique is doing diagrammatically. Alternatively, in this background field formulation or background field method, we can just, we don't care about these box diagrams, because we can just work with this effective vertex, where we use the background photon here as mediator in this expression. Okay, if you use this quantum Feynman background gauge, Feynman quantum gauge. Okay, so this is what we have been doing in our paper, because this is a very easy or like this calculation is very easy. So let's have a look at what actually changes. So in this background field formulation, actually everything remains the same except this triple gauge vertex, so the gamma VV, and this gamma V Goldstone vertex. Everything else is the same. And this triple gauge vertex, we just have to add these two terms. And for the photon vector boson Goldstone, this is actually just 0. So basically, if you just make this small replacement, we ensure that our result is gauge independent and it will also turn out to be UV convergent. So at the end of the day, computationally, this is extremely easy. And there's also this very recent example, again, about these electric dipole moments at 2-loop order in the 2x doublet models, but this time with all contributions, where they use the background field method to obtain a very nice gauge independent result. Okay, so let's go back to this amplitude, or this vector contribution. So we started with these one loop diagrams. Now if we use the background field method, you just have to replace basically this vertex here. And then you can use this form or this trick I told you earlier about, or you can extract the anapole moment from this one loop expression, and you find this contribution. And again, it's very neat because you explicitly see that for this AV to be non-zero, you need P violation. So these couplings should not be the same. Okay, let's again look at the plots. So these are very similar than before. But now the x-axis is the vector boson mass in units of dark matter mass. And here this green line corresponds to the W mass, so ATGeV. So the overall trend is the same basically. You get this huge enhancement once this vector boson mass is close to mass to the dark matter mass. And the overall amplitude is again dictated by the lightness of the internal fermion. Okay, so now this was the, let's say, model independent calculation. Now I can talk about the anapole moment of the lattice neutralino. So with this, let's consider some simplified scenarios. So let's talk about, sometimes they're referred to as minimal dark matter, because we basically only play with the gauge group. So we don't have any light scalars in our theory, so no light fermions. So the first situation, or the first case we can consider is that we have a pure bino, in which case dark matter is a SU2 left singlet. So in this case, this SU2L singlet doesn't have any interaction with the W or the X. So the anapole is expected to be small. The second situation is if you have a pure Higgsino. So this is a SU2L doublet. In this case, it turns out that these interactions it has with the W are parity conserving. So you don't expect any anapole. And then furthermore, you also have contributions from charged Higgs, but they turn out to be very small too. And then the last iteration is if you have a triplet under SU2 left, which corresponds to this pure Vino limit. In this case, unfortunately, the parity or the interactions with the W are also parity conserving. So this means that for these minimal dark matter setups, so if you have a singlet, doublet, or triplet under the SU2 left gauge group, the anapole is expected to be very small. So there are basically now two ways how you can increase the anapole.
So if you put a SU2 Higgs triplet, okay, this will be still small.
Yes.
Then consider the second case, and I replace the SU2 doublet with the triplet, a scalar triplet, in the superpotential, let's say. Then that will be a triplet, no? And so you have two more charge partners. There will be 1p0 T dash.
I don't know. It depends. I mean, basically here this is the argument is parity conservation. So it depends on how these interactions will look like. If they
It should be parity conserving as well.
Yeah.
Yeah, I see this.
Yeah. Okay, so basically as far as we know, there are these two options. So one is that we add light degrees of freedom, so that we go away from this minimal dark matter setup. And the other option is that we allow mixing. So if you have, for example, a Bino Higgsino, like this neutralino, then you don't have this problem anymore that you have parity conserving interactions. So let's talk about these two cases separately. So here I show this object one. So we add light scalars to the theory. In this case, we just add a light scalar partner of the tau, so a tau. So this first case is for pure Bino plus a light star, pure Higgsino plus a light star, and a pure Bino plus a light star. Okay, so these are scatter plots. X-axis is the mass of the neutralino, y-axis is the prediction of the anapole moment. Okay, there's just okay, let's start here maybe. So there are these empty regions which correspond to the pairs of masses which are excluded by lab or atlas. Nevertheless, for example, if we go to 100 GeV, the anapole can reach values up to 10 to the minus 6-ish. Then for the Higgsino, so it kind of a little bit depends on the ratio of the webs. So the larger this ratio is, the larger the anapole contribution, or the larger the anapole moment is. And then for the Vino, okay, it's kind of similar to the Vino. Here, just the difference is that, I mean, okay, also here, that the minimum mass is kind of constrained to the supersymmetry relationship between the masses of the Vino and the W.
You mean light scalar is tau you're talking about?
Yeah, exactly. Like in this case, we just have a star. So we considered only one loop diagram, tau and star.
But in general, like if you consider the MSSM scenario, if you consider 125 GHz, then loop and beta is kind of disfavored.
Yeah, this is just like a
yeah, I
ballpark,
understand.
like
If
yeah.
the Higgs mass bound, maybe you can get a preference there in the second plot.
Sure. But I will include the full MSSM later. I will talk about this too. So this is just like, let's go step by step. Let's see how we can increase this contribution. So here the point is just, I mean, like this Bino, Higgsino, or Vino-ness, that basically just fix your cover, your CLCR. And then you just have these this tau mass, for example, which which gives you this prediction. But yeah. Okay, so then the second case is that was that we allow mixing in this between different neutralinos. So in this case, we have the mixing between Vino and Higgsino. So here are some cases, or there's some structure. So these red points correspond to Vino-like scenarios in this situation. And here the anapole is kind of suppressed because you always have this heavy chargino in your spectrum, and this suppresses your loop basically. So here you don't have any light scalars. Here the anapole only comes from this vector contribution, from this W chargino basically in the loop. And here, because the chargino is heavy by construction, because we are in a Vino-like scenario, these red dots are typically kind of small. Then in contrast, these green points, they are larger, just because then you have this degeneracy between the lightest neutralino and the lightest chargino in the loop. And then the largest value here, I don't know if you can really see it, are these pink points, which come from a mixed scenario. So where they're like, mixed. Okay, then here this is the Vino-Higgsino scenario. So this is very much the same. So if it's purely Vino-like, it is suppressed. If it's Higgsino-like, it's a little larger, and the largest value is obtained if it's a mixed set. And then also you may have noticed that this Bino-Vino contribution is not here, or there's no plot for this here. And the fact is just that in this case, the anapole is actually expected to be extremely small due to parity-conserving couplings. Okay, now let's talk about the MSSM. So here I show a scatter plot of this 19-dimensional MSSM. So I let all the parameters at the high scale, I just scan through them kind of, and this is the result.
So it's still star, right? The x-axis, or
the x-axis is the mass of the neutralino.
neutralino, but okay,
Okay, so the x-axis is the mass of the lattice neutralino, the y-axis is the prediction for the anapole moment, and then these dots correspond to different likeness of this lattice neutralino. So red is Vino-like, blue Vino, green Higgsino-like, and pink mixed. So here I use constraints from lab, Z to invisible decay from the Higgs sector. So here we have 125 Higgs, LHC, and flavor physics. So this is kind of the, let's say, the natural ballpark within the MSSM, but I don't use any dark matter constraints. So the relic density is typically here underabundant. And yeah, also no direct detection experiments or anything like this is considered. So this is just to give, like, let's say, a ballpark in a reasonable UV theory.
Okay, so I mean, just a stupid question. So, is there a way to put experimental bound on this? What is it? Anapole.
Yeah. Yeah.
So, can you put a line on top of this curve? Or not?
Yes. Actually, this is the next topic.
I see.
How much time do I have?
Just 10 minutes or 15 minutes.
Okay. Okay, so let's then briefly talk about connection to direct circuits. So exactly, we're interested in, can we actually put limits now? Or can we somehow experimentally probe this anapole moment? So basically, now I'm going to talk about 3 different ways how this can be looked for in direct detection experiments. So the first one is nuclear scattering. So in this context, what people do, or what you can do, is that you decompose your relativistic operators, in this case the anapole operator. You express it in terms of these 14 independent non-relativistic operators. So this whole framework has been developed to exactly deal with this setup, let's say. So in this setup, you have an effective interaction Hamiltonian, which here you have the Wilson coefficients, then you have this isospin basis, and you have these 14 operators. So then based on this Hamiltonian, one can write down this cross-section. So the differential cross-section between dark matter and the nucleus, which is proportional to this matrix element squared. And this matrix element, or this expression here, is proportional to this sum here. This R are the dark matter response functions. So this is basically where all these Wilson coefficients will appear, plus kinematics. And then this W is the nuclear response function. So it's pretty cool because you can factorize dark matter physics from nuclear physics. And then this framework is very useful because once you know how you can decompose your relativistic operator into this basis, you can basically skip all the points and directly go to this cross-section formula and just substitute the Wilson coefficients you found in this expression. So in other words, you kind of have a dictionary between operators and the direct detection cross-section. Okay, so this is the first approach, how you can experimentally access this anapole. Then the second approach is about electron scattering. So there's a similar formalism to do this. It's a little bit different. So in this case, what you do is that you separate short scale physics, short scale and long range, short range, long range physics. And again, you have like an operator basis and the ionization rate. So now it depends on where this electron is. So it depends on the quantum numbers of the electron in the atom. Can be written as this velocity integral over the cross-section, the ionization cross-section. And this ionization cross-section is now proportional to an integral. So this Q is the electron momentum. And then you have this matrix element squared. And this matrix element squared, similar to before, can be expressed as a product of the dark matter physics, here the dark matter response function, and nuclear physics. But now, so this is a little bit more complicated because you have one additional integral, this Q integral, which comes from the fact that basically the dark matter momentum does not directly translate to the electron momentum. It depends on which shell the electron was. So this is where these nuclear response functions depend on multiple momentum. And the third aspect is Migdal. So it's very neat. The Migdal effect basically, so the idea is that after dark matter hits a nucleus, it can be like, and the energy is not enough such that the nucleus itself like causes a recoil, which then makes a signal in the detector, but it's kind of just like gets a little bit moved. Then the electron cloud needs to catch up, and this can lead to ionization. And in this context, the cross-section can be factorized like this. So you have the, let's say, standard nuclear, dark matter nuclear cross-section times an ionization probability. So this is the probability that basically this Migdal effect can occur. And the point here is, or this nice observation is, that this actually extends the reach of nuclear recoil experiments down to the GeV scale. So here I show some plots from this paper, basically where they show the recoil spectrum, so the expected recoil spectrum for a fixed dark matter mass and some reference nuclear cross-section. And here, these different colors correspond to electrons being ejected from different shells. And so for 0.5 GeV, you don't expect any nuclear recoil. Nuclear recoil would correspond to this black line. So if you have a dark matter of 2 GeV, here there's some nuclear recoil crawling in, let's say. But still, you can see that these electrons coming from this Victor effect appear in the spectrum. So these are basically these three direct detection strategies. Okay, so all we need to know is how we write our electromagnetic moments in terms of these non-relativistic operators. So here I show this decomposition for the non-relativist, for the nuclear recoils. Okay, so the anapole is a combination of O8, O9. The electric dipole is just O11. The magnetic dipole is O1, O5, O4, and O6. Okay, the details are not so important, but that's just kind of what you need. So it's not so complicated, and based on this decomposition, you can basically write down the differential cross-section and the differential rate. And then a similar thing can be done for the electron recoils. Okay, so in this plot, I show the anapole moment, then all of these direct detection exclusion limits. So on the right-hand side of this plot, the nuclear recoils dominate. So here's xenon 1-ton nuclear recoil data. Here's pico, this brown one is pico nuclear recoil data. Then for around 1 GeV, the Migdal effect, in this case from dark side 50, gives the most dominant constraints. And then below 1 GeV, the electron recoils give the best constraints. Also in this plot, I show some other constraints, for example, from supernova 1987A. And there's also some collider limit from lab on the effective operator, which is here the anapole. Okay, then also he shows some dots. So this is basically a model prediction. So this corresponds to the scalar UV model I talked about earlier. Yeah, we also indicate if it is overabundant, so this would correspond to these gray points, or underabundant, which corresponds to these red points. And you can see none of these lines actually touch any of these model predictions, let's say. Okay, so now let's go to the last chapter, dipole moments of Dirac fermions. So far I talked about Majorana fermions. You only have the anapole moment in this case. For Dirac fermions, you also have the other moments. So a small reminder, so this is the same slide as earlier. You can have this decomposition. And I mentioned earlier, for the anapole case, if it's a Majorana fermion, all of them are zero apart from the anapole. If it's Dirac, this doesn't have to be the case. And in fact, because these dipole operators, for example, here this magnetic dipole operator, is a dimension 5 operator, you typically is expected to dominate over the anapole dimension 6 operator. So if it's Dirac, we are very much interested in studying the dipole moments. Okay, so these are some plots showing the result for the dipole moment. So in this case, for the scalar model, we have a tau. Okay, but that's not so, I don't want to focus on this now. Let's talk about this. So this is a very similar plot than before, but in this case for the magnetic dipole moment. So now we're talking about the Dirac fermion. And again, here are all these exclusion lines. So on the very right, there's the exclusion line from xenon 1-ton nuclear recoil data, dark side 50 Migdal effect, and then xenon 1-ton and xenon 10 electron recoil. So in this case, okay, there are also these model predictions. So again, you can see that for larger dark matter masses around, I don't know, 8, 9 GeV or so, nuclear recoil is dominant. Then for lower, between like 1 GeV, electron recoil are dominant, and in between, the Migdal effect gives the best constraints. And also the other thing is that these red points, which correspond to an underabundant dark matter, so it could exist, let's say, but they are very much constrained by these lines. And then, okay, this plot is again very similar. In this case, for the electric dipole moment. Okay, so the behavior is very similar. There are these different lines from nuclear recoil, from Migdal, and from electron recoils, and there's this model prediction. And here, basically, a lot of points are ruled out. And one observation which is very nice is that if you compare it again to this magnetic dipole moment, that the constraints for the electric dipole are way better. So here we go down to like 10 to the minus 9 or 10 to the minus 8 or so. And here we barely touch 10 to the minus 7. So the limits on the dipole moment is around 1 order of magnitude better than for the magnetic dipole moment. Okay, so this is gonna be the last slide. Let me briefly summarize what I have been talking about. Okay, so the general setup or the general idea is that dark matter could interact with the photon via its electromagnetic multipole moment. So this is experimentally not excluded at all. So it makes sense to study this. Explicitly, I talked about the calculation of two model-dependent contributions to the anapole moment of a Majorana fermion. One was the scalar contribution, and the other one was this vector contribution. I talked about this special treatment one has to use in order for this vector contribution to be physical, so background field method or pinch technique. I talked about simplified models. So spino, vino, xeno, or like what happens if you add a light scalar to these three cases and so on. So for the scalar situation, it was found that in this region of 100 GeV, so for dark matter masses of the order of 100 GeV, values for the anapole moment due to the scalar contribution of the order of 10 to the minus 6 were found. Meanwhile, for the vector contribution, it's 10 to the minus 8. So this is way smaller. Nevertheless, this is the only contribution which is present if there are no light scalars in the theory. Okay, then on these last plots I showed you, you could see that the anapole prediction, so within these simplified models, is not experimentally accessible yet, and that the situation is actually different for the dipole moment. So here, the simplified models are very well tested by the direct detection experiments. And I would like to thank you for your attention.
Thanks for a nice talk. Any question?
When you calculate the relic density, so could you show this? Yeah, for example, in this plot, this scattered plot for the relic density. So those points are obtained from tree level.
Yes.
Within that model.
Exactly. Yeah. So here I just consider. So here we work in this. I don't have it anywhere. So yeah, but yeah, it's like for this T-channel scalar mediator. So like the tau basically. Yeah, this one. Yeah. So in this model, you can have you can get the correct you can calculate the relic density just via this tree-level process with this T-channel in the T-channel mediator for the annihilation. Yeah. So I don't think I have the explicit formulas there, but yeah. So like I mean, the key point is for these plots, we don't consider the operator itself to generate the relic density or to be responsible for it. So we don't have any photon mediated annihilations, for example.
Is I think asked by Kevin previously, discontinuity in your. So what is the origin of this?
So actually, that's basically here. So this loop, so these anapole moments, they both depend at some point on this f. So I didn't write this down explicitly before, but here it is. And basically this log here is discontinuous at some point. So here you can see it here, it jumps. It has it makes a sign shift basically. Here it's positive and then here it's negative on the right hand side of this black line. So basically this is kind of what is happening in these plots. So in these plots I was showing the absolute value of the anapole contribution, but actually it changes sign, it flips. So this leads to this discontinuity. And also similar here, I think along kind of this line it's discontinuous. So this is for the scalar, this is for the vector contribution.
So this is from one diagram, right?
Yes, yes.
I thought the plot could have a concept. I mean, it could be how to say, there could be some concept where the the loop function is not differentiable at certain point. But still, I thought it's continuous, but it's not. So you are saying it's not.
Yeah, it looks like it. Yeah. Like there was this. Do I have the reference? Okay. Like in no. Okay, somewhere there's this reference by Kopp and collaborators. Yeah, in 2014. Loopy constraints of T-channel mediated dark matter, I think, was the paper. And they also noticed something similar, and their interpretation was that this corresponds to the case where the particles in a loop all get on shell at the same time, basically. So if like the scalar and the fermion are on shell, then you get this behavior. So this was their interpretation, I think. Yeah.
Well, and could you go one more question? Sorry. Previous slide. One more. So, just where is it? You are talking about magnetic. This anapole diagram. One photon exchange and the two photon exchange box diagram.
Okay. Yeah, so this one.
Yeah. So you are saying that on the first row, some of these two are gauge envelope.
Yes.
But if you ignore the box diagram, it's not.
Exactly, that's the statement. Yeah. Just considering this diagram, it's not necessarily gauge independent. The reason in this case, it depends on what is in here in the loop at some point. But in our case, the problem is this triple gauge vertex. This is gauge dependent. So basically, yeah, if you just write down these two diagrams, this is gauge dependent, and also UV divergent. So
could you show the diagram again? No, one more. Yeah, this diagram. So here, 1, 2, 3. 1, 2, 3. And then, okay. So they two types of data have the same order of e to the fourth power. So this is around e to the fourth electric coupling to the fourth power.
Let's check the result.
Okay, so
yeah, exactly. So here you get electric charge.
you have to attach it, yeah.
Okay, sorry, this is great.
Why you have only
So basically, because this is parameterized in these couplings here, VL, VR. So like, for example, in the MSSM, you would have like the weak gauge coupling or something appearing here. Maybe like, okay, I have the formulas for the MSSM in the backup. Yeah, okay, for example, here. So these are the couplings for the Giardino, and here you have like the weak gauge coupling, for example. So,
yeah, anyway, if we attach this if we attach this fermion line to the gammas, so no. I was a little bit confused because this pi gamma diagram, you don't have attached fermion attached side part.
Okay.
But in the box diagram, you have attached the external particle. Once you attach the external particle, then both two types of diagram have the same power of e to the fourth. Right?
I see what you mean. Okay.
If you look at just this,
it
looks like
okay.
In a different order.
Okay. Yeah. Okay. I see what you mean. So like here, there should also be this fine. Yeah. That's true. Yeah. So basically, this should be also.
Okay. Now.
Okay. So yeah. You're right. Yeah. But yeah, exactly. But the point is, like to make it explicit. So like here, if you only consider these vertex contributions, which are these, it's not enough. You also have to include this. So this is meant to be schematically read, not like as an explicit equation. But yeah, true. Technically, like to properly write it down, to properly do the calculation, you need like this final state here, or like initial final state of the target. Yeah.
Okay, thank you. Yeah, I got it.
Sorry, yeah, that's true. I didn't think about it. Thank you.
Any other question? Actually, I have a lot of questions, but just in this place, I'm going to ask you only one question.
Sure.
In your title, you said you were considering multiple expansion, something like that. Your talk title, right?
My talk title?
Or multiple something.
Yeah.
Yeah. By the way, if we consider quantum field theory, then we obtain only, as you told me, electric charge radius term and anapole term and electric dipole term and magnetic dipole term. That's all, right?
For the fermion, yes.
Yeah, for fermions. But in this case, what is the meaning of multiples? In your talk, you only consider spin 1 over 2, right?
Yes.
Yeah. Then what is the meaning of multiples in your talk?
I mean, these are like the lowest order.
I lost order multiples. Okay,
Yeah.
I got it.
I mean, with multiples, I meant, let's say, this whole family of multiples. So instead of just tree level, you're looking at the multiples. So like you're looking at the dipoles and the anapole moment, for example, instead of tree level, which corresponds to like the 0th order, right? So you go one step above.
Okay, I got it.
Oh, one more clarification.
Sure.
So, you know, when you have a charge distribution and the current distribution at classical level, EDM of charge distribution is roughly electric charge times the size of the distribution, right? Roughly.
Maybe.
Electric charge times the size of the charge distribution. E times some linear size. Right? And for the quadratic dipole moment, it's electric charge 곱하기 size square, roughly speaking. Dimensionally, it should.
Okay, yeah.
Okay. And this magnetic moment is basically current times the area of the loop, the current makes. Then what is the, I mean, in this kind of a picture, what is the size of the anapole, roughly?
Plus.
Yeah. Then this,
You don't have to answer right now. I will be here tomorrow and so.
yeah.
So
Yeah,
this is the.
Yeah, it's hard to get a grasp what this is supposed to be, I think, but this is kind of this explanation which people typically have. So yeah, if you have like this torus with this current flowing around the, well, this axis here, yeah, I don't have a better answer.
So this, let me check what this paper says.
So in this paper, it's actually a condensed matter paper, if I remember correctly.
I have read this paper.
Oh.
Yeah. And also I have seen this figure. Yeah, because this is the paper explained very well. Yeah. Right.
Yeah, like on a classical level, right?
Yeah.
Exactly. They're doing very explicit calculations on a classical level in this classical picture. Yeah.
So you know this paper?
Yeah.
Oh, okay.
Yeah.
So he's also working on anapole.
Yeah.
Yeah, we
I
have
have
talked
seen
about that. Yeah. So as you can see, there is a perfect solenoid, right? Yeah. So, in principle, anapole can generate the out-of-bomb effect. Yeah. This is it. Actually, classically, it's not physical. Anapole. Yeah, anapole is. Yeah, it's very difficult to explain in classical language. Yeah.
But if you look at the direction, it just looks like a current loop.
Yeah.
Right.
Yeah, there's nothing in the there's nothing in the this hole. Yeah, as you
So what I'm
know.
trying to say, if you look at a current carrying loop, it just gives you a dipole.
Yeah.
Pointing vector. So if you look at the resultant vector,
Yeah, kind of vector. Yeah.
So it just resembles the normal dipole with the where weight goes to zero.
Yeah.
So
As you know, the magnetic field is only in the solenoid.
yes,
Yeah.
So
Okay, thank
and
you.
that is probably the reason why what you asked about the spin, because
Mm.
just that the vector that acts like, because in quantum spin you do not have those kind of picture, it is intrinsic spin, but
Yeah.
you can have this picture.
Yeah.
So this
Yeah.
is why in quantum level they act the same way.
Yeah. Okay, if there is no question anymore, let's thanks to speaker again.
Thanks for coming.
Yeah. And
I
we
think this month many people are traveling around, so not so many audience.
Mm.
Anyway,
And we have a seminar dinner. So, who will you join us?
Where that depends. Where are you going?
We need to choose now from now
I see. Yeah, you decide, then tell me, then I'll tell you.
on.
Yeah, because I don't eat some of the things, so
Yeah.
What?
I don't eat some of the things, so
Oh yeah.
Yeah.
So you guys
You
decide.
you can decide. I'll join tomorrow together with another. Yeah, sorry.
Then, just I'm going to if you.
Sorry, I'll.
Yeah, no, okay. Yeah, okay. I think just only you and I go to seminar dinner.
Sure. We can discuss anapole moments.
Yeah.
Yeah, I think you have
Yeah.
a lot of things to talk about.
Yeah. Just we can only we can go to seminar dinner. Yeah.
So please ask him what he wants.
Yeah. Yes.
Okay.
Okay.